Why can you see the things around you? It's because there's light. At night, if there's no lighting, if the sky is overcast or if there's a new moon, you won't see anything. The sun, stars, flames, and lamps all give out light. Objects that give out light are called luminous objects. Objects that do not give out light are called non-luminous objects.
The moon itself does not give out light. The moon is bright because it reflects the light that the sun shines on it. It is this reflection that we can see the moon. Most objects do not give out light themselves. We can see them because these non-luminous objects reflect the light that falls on their surfaces. An example is the retroreflective material used on the uniforms of the police and on road signs. When the light from a torch or headlights falls on this reflective material, the material reflects the light back. The uniform and road signs can then be easily seen by drivers.
We know that light travels in a straight line. Make different shapes with your hands in front of a light source. You'll see lively images of dogs, ducks, and birds on the wall. If light didn't travel in a straight line, there would be no shadow. Over 2,000 years ago, the Chinese were already using a pinhole to create images. The way to do this is to fix a board of wood against a large window and make a pinhole in the board. A picture will then appear on the opposite wall. This is known as a pinhole image.
Both a pinhole image and a pinhole camera are based on the fact that light travels in a straight line. We can use a shoebox and a piece of tracing paper to make a pinhole camera.
If light were not reflected when it traveled through space, we wouldn't see the light. There are dust particles in the air medium. These particles reflect the light, so we can see the path of the light as it travels through air. We can see light beams from strong light or from lasers when the light is reflected by the dust particles. As only a very small amount of dust particles is present in outer space, we cannot see light as it travels through space.
The glass container is filled with water. Now I flash a torch at it. It seems that there's no light traveling through the container. But if we put milk powder into the water, we can gradually see the light beam. The light is reflected off the small milk particles. What we see are illuminated milk particles. Normally, we draw the sun in this way. These straight lines represent the light rays from the sun. Now I draw two straight lines to represent light rays and use arrows to show the direction of travel.
Light always propagates in a straight line in a medium such as air. But when it meets a smooth surface, it will be reflected. Just like a ping-pong ball rebounding off a wall. This is known as reflection of light.
Hold the mirror obliquely to catch the incoming light beam. Now move the mirror and reflect the light beam onto the wall. We can see that a slight movement of the mirror makes a great difference. The reflected light spot moves a great distance across the wall. That's the relationship between the reflected ray and the incident ray. Put a sheet of white paper on the table and place a ray box above it. The light beam from the ray box forms a bright line on the paper. Put a rectangular mirror in the path of the light beam, and the reflected beam will appear on the paper. Change the angle of the mirror, and the reflected beam will also change its direction.
Draw a straight line on the paper along the plane of the mirror. This is the position of the reflective surface. Use a few pins to locate the paths of the incident ray and reflected ray. Then use a pencil and a ruler to draw the incident and reflected rays on the paper as marked by the pinholes. The incident ray hits the mirror at the point of incidence. Draw a line perpendicular to the reflective surface at the point of incidence. This line is called the normal. The angle between the incident ray and the normal is the angle of incidence. The angle between the reflected ray and the normal is the angle of reflection. Use a protractor to measure these angles. We can see that the angle of reflection is equal to the angle of incidence. If we change the angle between the incident ray and the mirror, we find that the two angles are always equal. This is known as the law of reflection.
In a dark environment, use a light torch to illuminate a mirror and a piece of paper. Guess which of the objects is brighter? It turns out that the mirror looks dark, while the paper is very bright.
When light falls on a smooth mirror plane, the angles of incidence of all rays are the same. The angles of reflection will naturally be the same too. The light will then be reflected regularly. None of the reflected rays will enter your eyes. When a beam of light falls on a piece of paper, the light rays are reflected in different directions because the surface of the paper is not regular. We can then see the illuminated paper from any direction.
When we look at things, we are used to tracing the source of light from an object along a straight line. The candle we see now is only its image. The light from the candle is reflected by the mirror into our eyes. So we get the impression that the light comes from a point behind the mirror, which we call an image.
Let the divergent rays from a ray box fall on a plane mirror. Extend the reflected rays backwards to locate the image of the light bulb in the ray box. The reflected rays seem to have come out from this image, but in fact they have not. This kind of image is thus known as a virtual image.
This is a piece of flat glass set up on the table. I place a lit candle in front of this piece of glass and place a glass container behind the piece of glass. Now I fill the glass container with water. Remember, these two objects must be at equal distances from the flat piece of glass in a dark environment. When we watch from the side of the candle, we will see a strange phenomenon. The candle is burning underwater. This experiment shows that the object in front of a mirror can form a virtual image behind the mirror. The distance between the object and the mirror is the same as the distance between the virtual image and the mirror. Take two candles of the same size. Light one and put it in front of a piece of flat glass. Put the other unlit candle behind the glass. Move the unlit candle until it appears, from all angles, to overlap with the virtual image of the lit candle, so that it too looks as if it has been lit. This experiment shows that the virtual image and the real objects are of the same size.
Have you noticed that the letters on an ambulance are written the wrong way round? In other words, they are laterally inverted so that the driver in front of the ambulance can read the word in its normal form when looking in his rearview mirror. Place a card with the word light written on it on the table. Stand a mirror on the card. When we look at the mirror, we will see that all the letters in the mirror are laterally inverted.
The image formed by a plane mirror is erect but laterally inverted. So the left hand becomes the right hand, and the left eye becomes the right eye. The image in the mirror sometimes creates interesting illusions. Because of gravity, you may not believe that I can lift both legs from the ground and float in the air. But how would you explain what you see now? A mirror can form an image. Two mirrors can form 2, 3, 4 or more images. These images are formed by the multiple reflections of light between two mirrors. An image is formed when light is reflected once by the mirror. The smaller the angle between the mirrors, the greater the number of reflections of light between the mirrors, and the greater number of virtual images formed. A kaleidoscope is constructed using this principle.
As light travels in a straight line, how can we see things beyond the wall? In ancient China, there was often a large bronze mirror suspended at an angle below the eaves of a house. If we put a basin of water on the ground, we can see the things outside the house by means of reflection.
I can't see the things behind this wall, but a periscope can help. A periscope is made of two plane mirrors of exactly the same size. The mirrors are placed at an angle at the top and at the bottom of a rectangular box, parallel to each other. The angle between each of the mirrors and the box should be 45 degrees.
Light goes into the box through the window at the top. The light rays turn 90 degrees at each mirror and go into our eyes. Moreover, after 2 reflections, the virtual image that we see is no longer laterally inverted. Periscopes are fixed in double-decker buses to allow the driver to see what's happening on the upper deck. Periscopes are also fixed in submarines to allow the crew underwater to see things on the surface. Why does a swimming pool look shallower than it really is? Why does a word seem larger when viewed through a block of glass? Immerse half a chopstick in water. Look carefully at the chopstick. Is there anything special about it? Now you don't see any coin in the bowl. Keep your head in the present position. Pour water gradually into the bowl. Gradually, gradually. You see the coin. When the light rays from the coin go from water into air, they change their direction at the boundary of the water and the air. Thus they go into your eyes, and so you see the coin. When a light beam from a ray box enters a glass block, it changes its direction. This is known as refraction. The beam is refracted again when the light leaves the glass block. A prism is made of glass or some other transparent material. When a light beam falls on a surface of a prism, light will go into the glass and be refracted. As it leaves the prism to go back into the air from another surface, the ray of light changes in direction and bends towards the base of the prism. A swimming pool appearing to be shallower is another example of the refraction of light. Light's reflected from the bottom of the swimming pool. When the light rays pass from water into air, they bend away from the normal. When the light enters the eyes will trace the source of rays along a straight line. As a result of refraction, the swimming pool looks shallower than it really is.
When we look at a goldfish in an aquarium, it looks a bit larger in size and a bit nearer. How would we look like in the eyes of the goldfish? When light rays go from air into the water, they go into an optically denser medium. The rays will bend towards the normal. So from the point of view of the goldfish, we appear smaller and farther away than we really are.
In the morning, when we see the sun rising above the horizon, actually it's still below the horizon, as light rays from the sun are refracted on passing through the atmosphere. In the evening, when we see the sun approaching the horizon, actually it's already below the horizon.